Alright, so this video is dealing with Unit 7, so this one's shorter than the last two, most likely, in terms of the video length. But we're dealing with molecular geometry. So, you can see there are a couple different things I asked you to fill out. You had to draw the Lewis structure, you had to tell me what the molecular geometry was, tell me whether the molecule was polar or nonpolar, and then decide about the hybridization. So, I'll go through the first one in a little bit more detail, and then I'll try and go through the next a little bit quicker, but we'll be doing questions 19 through 25. Okay, so your first step, anytime you're doing a molecular geometry question, should always be to calculate the total number of valence electrons. Okay, so if you look on the periodic table, you'll see that carbon is in group 14. So if you remember our trick, we said that that meant that it had 4 valence electrons. Okay, so we'll add 4 for the carbon, plus there are 2 oxygens there, and oxygen's in group 16, so they all have 6 valence electrons. But if there are 2 of them, we multiply it, so that gives us a grand total of 16 electrons. So that means we only have 16 to work with, no more, no less. Okay? So now when we go to draw the Lewis structure, our first step is to pick your central atom. There were a couple rules for picking central atoms. We said if you have one of something, that's usually the center. We also said that hydrogen would never be the center. And the other giveaway here is we said if you have carbon, it will always be the center. So our carbon will be our central atom. The first thing we're going to do is connect it to those outer ones. Now keep in mind that when I do that, each of these dashes represent 2 electrons, or 2 shared electrons between the atoms. Okay? So we've used up 4 of our 16. Once you connect them, the next step is always to fill the outer elements first. So we've used up 4. Each of the oxygens already has 2 from the sharing, so they need 6 more. So we've used 2, 4, 6, 8. And then over here we have 10 already bonded, 12, 14, 16. Okay, let me clean this up a little bit. There, so we have our 16 total electrons used, right? 2, 4, 6, 8, 10, 12, 14, 16. So we've used all 16. Our last step is always to check, is everything happy? If we look at these outer elements, they have 6 plus 2 is 8, 6 plus 2 is 8, so those are happy. The problem is our carbon only has 4. 2 plus 2 is 4, but it needs to have 8. I don't have any more electrons, so I can't just put them on the central atom. So here's where we run into the case where if we don't have enough electrons, we need to subtract them from the outer elements and share them between the 2 instead. So if I take away 2 electrons from there and 2 electrons from there, and instead share them between the atoms, I end up with double bonds. Now if we count everything, our oxygen still have 8, 2, 4, 6, 8, 2, 4, 6, 8, and our carbon now has 8 as well, 2, 4, 6, 8. Okay, so that's our Lewis structure. Now looking at our molecular geometry, as far as the name goes, we were using that AXE notation kind of as a way to help us. So there's always one central atom, A. I have 2 O's attached to the center, so that's 2 attached atoms, so we'll say X2. And E's would be lone pairs of electrons. There are no lone pairs of electrons in the central atom, so we're just going to stop at AX2, which would make this thing linear. Alright, the other things it asks for, it says the shape, so if you were to draw this in 3D, it's basically going to look just like the Lewis structure over on the left, but it also asks for the bond angle. This thing is linear, and if you think about a linear molecule, that means it's a straight line, so that bond angle would be 180 degrees. Okay? Next up, it asks if it's polar versus nonpolar. So, polarity has to do with how this is balanced or shared. Since the 2 oxygens attached to the center are the same, that means they're both pulling on the electrons in these double bonds with equal strength, so this is going to be pretty balanced. So we would say that this thing is nonpolar. Okay, it's not pulled. Right? Remember, polar means polar means uneven, nonpolar means balanced out or even. Okay? And last but not least, we have hybridization. So hybridization, remember, has to go back a little bit to our light unit. In our light unit, we mentioned that anytime you drew an orbital diagram, we said that S sublevels always had just one box. Oops. Right, S has always just had 1 orbital. P's had 3. D's were 5. And then F's, running out of space there, but F's would be 7. Okay? So when we're doing hybridization, what we're doing is basically figuring out, based on the number of attachments, how many orbitals do we have to hybridize. Now, the concept of understanding hybridization is pretty tough, but answering the question is pretty straightforward. All you have to do is go back to the AXE notation you drew before, and whatever the sum of X plus E is, that's how many orbitals you use. Okay? So here, I just have 2 attachments. So what we'll do is we'll fill up the S first, so we took care of that one. And then next step would be P's. So then we'd have 2 P's. So our hybridization is sp2. And that's it. Oops, actually, I lied to you there. Sorry, guys. First thing we would do is S, but then we need a grand total of 2 attachments. So just 1 p orbital, because S plus p gives us 2, and then 2 from the x2. Okay? So there we are. This next couple we'll go through a little bit quicker. So just follow along. Alright, so starting with BF3, first thing, our total number of electrons. So where would we get that? Boron would provide 3. Each of the fluorines would provide 7. So grand total, that would give us 24 electrons. Boron's our central atom because we only have 1 of them. So we make our connections. That's 6 electrons. We have 24 to go. So 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. Okay, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 22, 24. Yep, you've got 24 there. Now, normally we would look at this and say, hey, that center boron only has 6, it should have 8, let's make a double bond. But boron is one of the exceptions, that it's a reduced octet. It's okay with 6 electrons. So we're actually done our Lewis structure just as it is. So if we move into our next column, we have our central atom. We also have 3 attachments to the central atom that are all atoms. So we just say AX3, and there are no lone pairs of electrons, so we don't have any E's. So what would something that's AX3 be called? This would be what we would call trigonal planar. Alright, so that would be our name. Remember, the AXE notation is just a means to an end. It doesn't actually mean anything. The name that I put in the box would be the actual molecular geometry. The angles. This thing is essentially a circle divided into thirds, so each of those fluorines would be 120 degrees from one another. Okay. As far as polarity goes, since all those fluorines are the same, they would have the same electronegativity difference, so they're all pulling on the boron with equal strength. This would also be nonpolar, basically because everything on the outside is the same. And then for our hybridization, there were 3 total attachments, right? So we need 3 total orbitals. So we'll have the 1 s orbital, and then we'll include 2 p's. That could have gone as high as 3 for the exponent on the 3, but we only needed 2. Okay? Next up, CHCl3. So same thing. Total number of electrons first. So we'd have 4 plus 1 plus 7 times 3. So that gives us 26. Central atom in this case is carbon, because we said if you have carbon, it'll always be the center. Alright, after we pick our central atom and connect everything, that used up 8 of our 26 electrons. So next we fill the outer elements first. Now keep in mind, hydrogens only need 2 electrons, so this hydrogen at the top here is fine just with that 2, but all the chlorines still need some extras. So we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26. So I've used up all 26 of the electrons. Now let's just see if everything's happy. Our carbon in the center is surrounded by 8 electrons, so that's good. Our hydrogen has 2. Each of our chlorines have 6 lone pairs and 2 shared, so they're good with 8. So that is what our Lewis structure would look like. Okay. Now for our AXE notation. We have our central atom, we have 4 attached atoms to it and no lone pairs of electrons. So something that's AX4 is better known as a tetrahedral. Remember, you are responsible for memorizing 6 of the molecular geometries. The other 6 are in the reference book, the expanded octets. As far as the 3D shape, this one might be a little bit tougher to sketch here, but it would look something like this. Those 3 would all be in the same plane. These would be at the bottom, basically like a pyramid with something sticking out of the top. And then our bond angles in a tetrahedral, all of them are 109.5 degrees. Okay, so there we are. As far as polarity goes, since everything attached to the center is not the same, this thing would indeed be polar. It would be pulled because those 3 chlorines have different electronegativities than the hydrogens. For our hybridization, if we have 4 total attachments, we'd have 1 s orbital, and we'd need 3 p orbitals. If these 4 things combine, we get a tetrahedral. Okay, so there's the first 3. Moving on to the remaining 4. Again, we'll go through these a little bit quicker. Starting with this first one, BeF2, we'd get 2 electrons from the beryllium, 7 times 2 from the fluorines, again, all because of the valence electrons, so that would give us a grand total of 16. Beryllium would be our center because we only have 1 of them. So if we connect everything, it would look like that. If we use up 4, we still need to do the remaining 16. So this would be 6, 8, 10. This would be 12, 14, 16. Sorry, we're running over a little bit there. This, again, would not form double bonds because beryllium is one of the exceptions. Beryllium and boron are the two that are okay with less than 8 electrons. So we're actually going to leave this just as it is. This would be AX2, like carbon dioxide, making this thing linear. So once again, our bond angles would be 180 degrees. This thing would still be nonpolar because the 2 fluorines on the outside are the same. And this thing would still be sp, 2 total attachments, so 2 total hybrid orbitals. Okay. If we look at XeF4, we'd get 8 from the xenon, 7 times 4 from the fluorines. That gives you a grand total of 36 electrons. Xenon would be the center because we only have 1 of them. So if we attach everything, this takes up 8 of our 36. So then we'd start filling the octets of those fluorines. So that'd be 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. So we've used up 32 electrons. We have 36 total, though, so we have 4 more to go. If you fill up all the outsides and there are still extras, remember the rule was that extra electrons go on the central atom. So here's where in our AXE notation, we're going to be changing it up a bit now. Instead of just X's, this would be AX4, because of the 4 attached fluorines, E2, because remember the E's correspond to these lone pairs of electrons on the central atom. So this thing, if we look at the name, this thing would be square planar. I will not ask you to draw this one in 3D, but essentially it would be a flat square with the fluorines as the corners, and then 2 electron pairs sticking out of the top and bottom of the molecule. Okay? This thing would, normally you would think this would be polar, because anytime you have lone pairs of electrons in the center, we tend to say that that thing would be polar. But this is one of the weird exceptions, where if you draw this one in 3D, since 1 electron pair is coming out of the top and 1 electron pair is coming out of the bottom, they are exactly opposite, so they're sort of canceling each other out. So this thing actually is nonpolar. It's one of the weird exceptions where just because there's lone pairs of electrons, they are symmetric, so it's actually still balanced. Okay? And then as far as hybridization goes, we have 6 total attachments, so we need 6 total orbitals. So we'll use the 1s, we'll use all 3 of the p's, that takes up 4, so 2 more, move on to d, and we only need 2 of them. So this would be sp3d2 hybridized. 424, we now would see we get 1 from each of the hydrogens plus the 6. We also have this positive charge. Positive charges, remember, come about because you lost an electron. So we're actually going to be subtracting 1 from the total. So if you do 3 plus 6 minus 1, this gives you 8 electrons. Our central atom would be oxygen because we only have 1 of them, and because we said hydrogen would never be a central atom. So doing that used up 6 of our 8. Normally we would fill the outer ones, but the hydrogens, remember, are all okay with 2 electrons, so those are done. The 2 extras would then go right here on the oxygen. The last thing you need to remember, because this had a charge, we will put this thing in brackets with the charge outside of it. Okay? So for our AXE notation, this would be AX3E, because we have 3 attached atoms, those 3 hydrogens, and then 1 lone pair of electrons. Remember, it's lone pairs, not single electrons. So something that's AX3E is better known as a trigonal pyramid. Alright, it's like a 3D pyramid with an electron pair sticking out of the top of it. Okay. If you were to draw this in 3D, it would look roughly like this. I'll draw it off to the side tiny. We'd have this, kind of like a tetrahedral we saw before. Kind of like that. Okay. If you're curious about the square planar one as well from the previous problem, I'll sketch that over here to the side while we're there. These fluorines would stick out towards you, these fluorines would go back into the page, and then you'd have an electron pair coming out of the top and the bottom. Okay? So there we are. As far as polarity goes, this particular molecule is polar because of this lone pair of electrons on the oxygen not being balanced by anything else. There are 4 total attachments, so our hybridization would be sp3, just like the tetrahedral earlier. Okay? And then our last one. Alright, so NO2, we get 5 electrons from the nitrogen, 6 from each of the hydrogens, plus 1 because of that negative charge, which means, remember, we have an extra electron. So that means 18 total. So nitrogen's our center because we only have 1. Whoops. So there we go, that used up 4. So then we would go 6, 8, 10, 12, 14, 16. We have 2 extras, so if you have extras, they always go on the central atom. But now if we reassess and take a look at our octet rule here, both of the oxygens are happy with their 8 electrons, 6 plus 2, but our nitrogen has 2, 4, 6, so it needs an extra. So here's an example of something that displays resonance, because once we move one of the electron pairs, it doesn't really matter which side we do this to though, our Lewis structure is going to look roughly like this. Remember, we do need to put it in brackets with the charge. I'm running out of space here, but if we were to draw the resonance structure, it would be the same thing except the double bond would be made to the other oxygen. Okay? In reality, this thing kind of spreads the electron density between both of the double bonds here, but that's roughly what it would look like. Okay? As far as our AXE notation, this would be AX2E, 2 attached atoms, 1 lone pair, and this would be known as a bent structure. Okay? Because of this lone pair on the top there, this thing would indeed be polar. And since we have 3 total attachments, this would be sp2 hybridized. 1 s, 2 p's gives you 3. Okay? So sort of a crash course on our molecular geometry there. If you have other questions or if this still is a little bit confusing, feel free to come see me before the final. I will try and help you as much as I can. Okay? Feel free to replay this as much as you need. Our next video will be looking at the Unit 8 questions on gas laws.